that you guys don't have to look at all the details. I'll label these based on what they are. All right, so this is now going to be more stream ciphers. Okay, so we were talking about the cipher feedback mode, CFB mode of operation that you would have either AES or DES, right? And we've seen how it is this idea of a thing that's accumulating as a key, and you're XORing it as the plain text is feeding in, right? All right, and we talked, I think briefly maybe in the slides, if you go back, remember there's slides about what the difference was between block ciphers and stream ciphers, right? So this could be a question also on the exam. So we have, this is all still symmetric encryption. Symmetric encryption. Okay, and here we have, you know, let's say block ciphers. Block cipher versus stream cipher. Okay, so what was the difference between these? Yeah, please. Block of some length. Yep.
And then stream cipher is bit by bit or by
byte, yeah. So you just a shorter thing of 1 byte. So basically, whereas here we're XORing blocks of plain text and cipher, here we're basically on a byte level. We are still XORing, and it's bytes of the key and bytes of the plain text message. Do you see that? Think about that though, because every byte that feeds into every byte of the key, let's say you have a movie, right? You have a movie, and this is the plain. That movie is pretty large, right? With the stream cipher, you're saying that every byte really that goes to be XORed with a byte of the movie should be different. That's problematic, right? Because that's effectively the one-time pad. Then we would need the whole key to be as long as the message. You guys see that? So that's problematic, but that's kind of what we're saying. So we kind of have to think about how it works. Okay, so we're going to formally define it now in terms of, once again, Claude Shannon's one-time pad, right? And what he defined back then. So let's provide a formal definition for the stream cipher. So stream cipher. Okay. All right, so basically the idea is that the motivation, let's say, for the stream cipher is that you're trying to make the one-time pad practical. Claude Shannon established that it was secure, right? If it's random truly, then if the key is the same length as the message, you have security, right? And so, but that's not practical to implement for a movie or whatever. So the motivation is, how do we make that practical? So making the one-time pad OTP practical. Okay, so that's the motivation. So the idea in the stream cipher is to replace the totally random key that Claude Shannon said you needed with a pseudo-random key. Okay, pseudo-random. So we can do that, right? You use something like that every day when you log into your university thing, right? You have a thing on your phone that gives you a code, and that code is constantly generating 6 numbers, right? That app, I mean. And so it's a similar algorithm, okay? So it's changing, but it's a sequence, and all of that is generated through an algorithm. But what it needs to have is that when you are assigned that app, they give you a key. that's just assigned with your name. And so that's kind of kept secret, and that's the seed that goes into this generator, what is called a pseudo-random generator. Okay, got it? All right, so that's the idea. So we'll formalize it now, but that's generally the idea. It's an algorithm basically, and it's used extensively for pretty much everything that we do, right? Because you log in with things like this all the time. So we replace, so the idea in the stream cipher is to replace, so we want to replace the totally random key, the random key, with a pseudo-random key. Pseudo-random key. Okay, so that's the idea. And the pseudo-random key, will the pseudo-random key need to be as long as the message? Okay. It's just true. Actually, the way that I worded it, because it does repeat, but you would want it to be as long as the message, although it can repeat. But once it repeats, that's a weakness. Okay, so that's because then what's going to happen, an attacker could have two ciphers generated with the same pattern. And so at that point, they can start to try to break it somehow. Okay. Now, these are things that they do all the time. So they're actively trying to break AES. And so obviously that, they'll try that. All right. But anyway, so that's the idea. So now let's define it. These are usually called, so if you come across these, they're sometimes called PRGs. And it's a well-known function used for a lot of things. People are constantly using functions like this. So this is the pseudo-random generator. Pseudo-random generator. Okay. So basically a pseudo-random function, the pseudo-random generator is a function. It's a function. Let's call it G, that takes a seed and produces a pseudo-random key. Okay, so the definition of it is G is going to take basically a seed, which is, oh, sorry, not two. S, this should be S. Okay, so that's basically it. And given that, is going to generate another sequence of zeros and ones of size n, where n is much, much bigger than S. That's basically the definition. Okay, very fancy words to say. You get a sequence of zeros and ones of a very small size, and with that, through an algorithm, a function, you get a sequence of zeros and ones that is much, much larger, because we now need it to be really large, possibly preferably as large as the message itself. Okay, so that's what the pseudo-random, with this, then we can build the algorithm basically, because this would meet the condition. So again, a pseudo-random generator is a function, G, that takes the seed. So this is the seed, right? As defined, so I can probably say seed is. That's the seed, right? So zeros and ones of size S, which is a small, this just means greater than, and when you put two, it just means much greater than. Okay. So it takes a seed of length S of zeros and ones. And so therefore, the function G maps the seed string to a much larger pseudo-random key. Okay, and that's why it's called pseudo-random. Now the function G is deterministic. So this is, you guys know what, the difference between deterministic and random, right? So deterministic is like predictable, like computers are predictable, right? Because they're based on algorithms. But initially, the algorithm will have an initial value that should be as random as possible, right? And so that's the seed usually. So you define a seed to feed the algorithm to spit out different things. Okay. All right. So so the G is deterministic. So let's define that. Because when you say it's deterministic, all that you're saying is that there's an algorithm involved. There's an algorithm that takes the seed and keeps producing bytes, basically. So the function G, is deterministic. It's deterministic, and only the seed is random. Another way of thinking about this is, let's say for the app that you guys use to log into your email and stuff every day to PNW, you all use the same algorithm, basically, right? So it's deterministic, but it's secure still because the seed is different for all of you. That's what is, when they create it in the system, it generates a seed for you, and then it's almost with some certainty guaranteed to be secure. Got it? All right, good. All right, so that's the definition of stream cipher. Let's just do like a little bit more. Oh, did it? Oh, I'm sorry. I don't know if it's that I keep pressing a button here. Oh, there we go. Great. Thanks. Okay, so we were saying, basically, so if we want to think of this as a diagram, this is going to be the key over here, K, right? And then we have the K is going to be expanded into a sequence. And really, the sequence can go on for a long time because it's really a function that, given a key, generates this stream of bits, okay? So then what's going to happen is if we do the XOR operation, we have a message of size M. Now let's give it a fairly long sequence. And then you want to, you have a key probably of very small size, but then because you have the generator, then you make a generator such as this, and then now you are able to XOR these on a byte per byte basis. Okay, effectively having this. So now the functions are, to conclude, so the functions are to get a cipher, the encryption with K and M. When you're doing a stream cipher, I'll just put stream down here. Stream cipher, this would be equal, or defined as, so you're going to define it as an M XOR and then G K, basically, and that's it. So that gives you what you need, but it's, at the end of the day, it's just an XOR operation of equaling. And of course, this function needs to be on both sides of like encryption and decryption, just like before. So that doesn't change. Okay. And then finally, for the decryption of K, and of course, this time the cipher. So you define this as the cipher right? XOR G K. You guys see that? Do you agree? And that would give you what over here? The message. Right? And that's it. Any questions? Make sense? All right, so you should be able to implement this algorithm, I think. Right? So what's the challenge? Probably defining the deterministic generator. Okay, it would just generate zeros and ones, etc. for your data, but you need to have the function. Okay, any questions? We might look at a problem later, but not right now. I was going to give you another one, but this is I'll leave this for something more fun, like a homework or something. All right. Yeah, so I think that should be stream ciphers. I think we're moving well. Oh, I guess, yeah, there's the diagram, right? Let's do the diagram. Forgot about that. All right, so the diagram for the stream cipher, we can kind of maybe wrap up with this section. So the diagram of the stream cipher would be something like this. So you have the plain text, right? You have the plain text, and then you have a byte stream. So you have to send the message 1 byte at a time, okay? And that's going to go in here and get XORed. Now the key, of course, is the seed, and that's going to feed into the PRG, right? The pseudo random generator, which is going to send things per byte as well. Okay, do you guys see that? Does this make sense? So now this will give you the cipher byte. Which is going to be sent through the channel. Okay, and it goes into, so this is the encryption part, by the way. So this is encryption. So on this end now, we're going to do the decryption. And so that would be what? How would you draw this part, do you think? What are you getting here? You're getting the cipher byte. So do you think basically the PRG again on a per byte basis? The key is the same, right? You need to have it. And then that just gets XORed. And then now you get the plain byte. Make sense, guys? So it's the same thing. If you look, they're both aligned. So it's the plain byte with from the PRG, the byte, the pseudo random byte. They get XORed. You have the cipher byte, and then the cipher byte and the same byte, and you get the plain back. And it's very similar to what we had done before, where we have a cipher and a message, and then when we have or we have the key and the message, we get a cipher, and then we have the cipher and the key, we get back the message. Any questions on this one? Oh yeah, please go ahead.
So the key going into the PRG that creates the pseudo random key?
Yes, it creates. So this is a function that just generates bytes. It's a good way of thinking. So it's like, think of it as there's a function here. You have a key, and that's a starting point for a for loop, right? And that for loop, what's it doing every time? A byte, then another byte, then another byte, and another byte. Just keeps sending bytes, right? And then what you're gonna do is you have a message, a plain text message, and you're gonna break it into bytes. And so they get XORed, the next byte gets XORed, right? And so on. So that they become a cipher when you do the XOR operation. Questions? Do you have an additional question?
So that's the plane and then the.
Yeah, so
random bytes, actually?
right, so we have, what's another way of putting it? So if this is the message, right? Let's say this is the message. So then you can take this piece, and that's a byte of the plain text message. You send it, right? That's that piece. But now you know that you're going to XOR something, so you need something to XOR with. In this case, we don't XOR with the key every time. Instead, what we do is we have a function called the generator, which takes a seed, of some size, let's say 128 bits or something, right? And what this function does is it's a for loop. Imagine inside the code is just a for loop, right? And the algorithm in this for loop is gonna generate blocks of the same size as this one, a byte, let's say, so that you may now XOR both of these together, the message and this pseudo-random byte key, to produce a cipher byte. And then what happens when you grab the next piece of the message? You also want, that's plain text. You want to XOR it, of course, but what do you XOR it with? Well, the pseudo-random number does not give you just a piece of the key. Instead, the key goes inside an algorithm like a for loop, and this for loop now will give you what? The next
sequence of it?
Yeah, exactly. Like the next, imagine that's why it's called a pseudo-random key, and it's giving you pieces of that gigantic pseudo-random key. But instead of creating a pseudo-random key that's gigantic and then cutting it in parts, the algorithm can just generate one part of it at a time. The code is built that way. So now the function would give you this. Remember, this is plain byte 1. This is plain byte 2. And then this would be what? Pseudo key byte 1, pseudo key byte 2. Yes.
So do you need a new seed for each of the bytes?
No, it's just one seed.
Okay.
And the generator generate. I think I get what your question, both your question is coming. So maybe let's think of it this way. And this might be a bit clearer. This is the message, and imagine it's really long, like a movie. Okay, imagine that's the message. That there's no problem, right? It's a movie or something. Movie. So this is your plain text. You need, for the one-time pad, Claude Shannon said that I need a random key as long as that message, but that's not practical or feasible. So what you might think happens is that you have a pseudo-random generator, pseudo-random generator, PRG, and it's some code with for loops and things like that, that takes in some key. And the key, this one should be random as much as possible, okay? So that's the key. And it could be something like 128 bits, but the movie is not 128 bits, as we know. So now imagine that what it does is, just given this key of 128 bits, it does something and it produces what? A new key, but because it's generated through a deterministic algorithm, we can't call it a key. It's not random. It's deterministic, right, in the sense, except for the seed. So that's why we call it a pseudo-random key. And that key, you can imagine, is literally, oops, sorry, that key. That came out, that key is the exact same length as the message. Okay, so erase that. So what is this? This is the pseudo random key. Do you see that? But it wasn't generated randomly, you know, of that length. Only the key, which is maybe to put it in contrast, we could say that the key is like that. That's the key. So this was expanded into that. How is it expanded? Through a function that takes this as input and now produces something that long, which is the same length as the message itself. Hopefully that makes sense, except that it's impractical to have to generate the whole thing of that big size, break it into blocks and then, or bytes, and then send it. And instead the algorithm can just generate this exact same sequence 1 byte at a time. Do you see that? So like it would do this byte, then that byte, that byte, that byte, but at the end it would be exactly this one here. But the algorithm can just generate them 1 byte at a time. There's no need to construct this to be that large. Did I answer your question? Maybe. Yeah, go ahead.
Okay, so if the key is 128 bits, does it just, the for loop, does it do the 1 byte and the next byte
Yeah.
and the next byte for each
Mhm.
piece of the message?
Yeah.
And so then when it gets to 128, it just starts over again from the beginning?
No, that
Like
not 100. So this can go, this can produce something that's really big. This could produce something that's really big, just taking this as an input. And it could just produce something really big.
So it would never go around again to the same key, like it would never start in the beginning, it would finish the key out.
It would, so the algorithm, I mean, it would generate it would try to generate a sequence that does not repeat. I can say that. That is definitely an objective. You wouldn't want to start here and then get to here and then start all over again the sequence, because then you would end up with this being the same as this. And so that's insecure. So you want this to become, you know, be as long as the message, basically. Okay, but that's the idea. So the algorithm starts with this, and then it's gonna do something in here to start producing bytes given that. So some algorithm. Okay, any other questions? So I mean, at some point we can look at, I don't have one PRG now, and I don't want to just like make up one. So, but we can take a look at the actual algorithm that does this. And it can be done. It's just a function. The key thing is it starts with the seed value, and then it just produces things coming out. Okay. I mean, you could create one that is like from, you know, 1 1 1 1 2 2 2 2 3 3 3 3 4 4 4 4 5 5 5 5. You see that? So then what do? I grab the key, XOR it, produce a cipher, and then compress that into a byte. See that? Then the next time I grab the 222, the same key, create the cipher, compress that into a byte. You see that, how I'm producing bytes that are different every time? What's the problem with my algorithm? There's a pattern, right? There's an obvious pattern of 1 1 1 2 2 2 3 3 3 4 4 4 5 5 5, and that's obviously a bad. So you'd have to make something that's a little bit better than this. But that's how you would produce it. I mean, you know, in essence. Okay. So obviously you want it to be a little bit better than that. Okay. So that, let's see. So that's the stream cipher. Well, I'll take a look to see if I have Yeah, so I don't have a stream cipher with me right now, so I'd have to look at one, and we can look at that later. All right, but what's important is to understand the definition, as I said, and this is really important. We can go back to the formalization of it. Right, so we have a key, and we're going to use a function to create a new sequence, which is going to be the pseudo-random key, and we want this to be as long as the message, except that we generate this on a per byte basis instead of generating byte, 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 and then putting it together to take it apart. Okay. All right, so that should be the stream cipher. And now I think we can move on to the data encryption standard. Okay, so that's so we'll start this one today. We probably won't finish it today because we're running out of time. So let me